In the last video, we looked at a binomial test for a population proportion, which we can think of as considering frequency data when there's just two categories. In this video, we're going to look at testing frequency data when there are more than two categories. And we're going to use something called a chi-squared goodness of fit test. So I've got a couple of examples that I'll run through. So this first one, we have data on the days of the week of births in the United States in 2016. And so we're just recording the day of the week that the birth occurred on. So for example, for the first observation, the birth happened on a Friday, the second one it was a Monday, the third one it was a Thursday, and so on. So the first thing I'm going to do is I'm going to create a factor from this variable. And the reason that I want to do this is because I want to have the days of the week be in the conventional order. So starting on Sunday, then Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. Otherwise, what R does by default is it puts categorical data in alphabetical order. And so this is a very common first step when you've got categorical data, is to create a factor, and then you can specify the levels, and then you can put the levels in whatever order makes sense for your particular application. So this is a very common first step when you're looking at categorical data like this. So once we've done that, then we can tabulate the data, and we can take a look at it. And so we can see that we've got 14 births that occurred on a Sunday, 26 that occurred on a Monday, and so on. And then we can also graph that. So we've got a bar chart here showing the frequencies for each day of the week. And you can see that we might expect the distribution to be pretty uniform across the days of the week. After all, there's no reason why a birth should occur on one day any more often than on another day. But there's quite a bit of variation here. So even taking into account that we've just got a random sample of births, we've got a very low count on Sunday, for example, much higher count on Friday. So maybe there's something going on there. So we're going to look at that, and we're going to do a chi-squared goodness of fit test. So this is a hypothesis test, and so as usual we need to go through our 4 steps. So the first step is to state the null and the alternative hypothesis. So our null hypothesis here is that the frequency of births on each day of the week is proportional to the number of times that day occurs in the year 2016. And then the alternative hypothesis is that the frequency of births each day of the week is not proportional to the number of times that day occurs in the year. And so if we look at a calendar for 2016, we can count the number of Sundays and Mondays and Tuesdays and so on. And so it turns out 2016 was a leap year, so we had 366 days in the year, and there were 52 Sundays, Mondays, Tuesdays, Wednesdays and Thursdays, and 53 Fridays and Saturdays. So these are our frequencies, or our proportions rather. And so the code that's used here is I'm going to use this test chi-squared.test, and again, as usual, I can always look up what that test is doing. So it tells me it's doing a Pearson's chi-squared test for count data. It gives a description, how to use the function, what the argument should be, details of what's going on, and then what the output is going to be, what the values are that we're going to get when we run this test. So let's do the test. And so We've done the first step of the hypothesis test, which is stating the null and the alternative hypothesis. The second step is to calculate the test statistic. So in this case, it's going to be a chi-squared test statistic, and I'm going to briefly explain where that comes from. So when we run this function here, this chi-squared test function, we get a few different pieces of output. So for example, we get the observed data, frequency data, and so that we've already looked at that. So this is 14 births on a Sunday, 26 on a Monday, and so on. And then we can also look at the expected frequencies for each day of the week. And these expected frequencies are if the null hypothesis was true. So if indeed the frequency of births on each day of the week is proportional to the number of times that day occurs in the year, then we would have a fraction 52 over 366 times the number of births in total, which I think was 180 in this case. Yeah, so if we did 52, well, I'll just do it so we can see exactly where that number's coming from. So if we did 52 divided by 366 and then did 180 times that, we'll get this expected frequency here for a Sunday. And it's the same expected frequency for Monday, Tuesday, Wednesday, and Thursday. For Friday, remember we had an extra day because of the leap year, so if I do that calculation times 53, I should get this number. So that's where these expected frequencies are coming from. And then the test statistic takes the difference between the observed and the expected. So for example, the difference between 14 and 25.57377 takes that difference, squares the difference, and does that for each day of the week, and then it adds up those so it's taking the observed minus expected squared, and then it divides by the expected number. Okay, so it'll be 14 minus 25.57377. It'll take that difference, square it, and then divide by the expected 25.57377. It'll do that for each day of the week, and then it'll add up all those scaled squared differences, and that's called the chi-squared statistic. So rather than having to do all that calculation by hand, we can just see what the result of doing that calculation is, and R tells us it's 15.795. So that is our test statistic. So that's step 2 of the hypothesis test. Step 3 is to calculate the p-value for this test statistic. So remember, the p-value is going to be the probability of observing a test statistic as extreme as this, or even more extreme if the null hypothesis was true. And so in this case, that p-value is going to be the upper tail area for a chi-square distribution. And so it'll be the area under the chi-squared curve to the right of 15.795. Chi-squared distributions are indexed by a degrees of freedom, and in this case it's telling us that the degrees of freedom for the chi-squared distribution that we need in this case is 6. You might wonder where that's coming from. That's coming from the fact that we've got 7 days of the week, and so the degrees of freedom is always 1 fewer than the number of categories for this particular chi-squared goodness of fit test. So then what R does is it does a calculation. It figures out the upper tail area for a chi-squared distribution with 6 degrees of freedom to the right of 15.795, and it does that calculation for us, so we don't have to worry about any other pieces of code, and it tells us that p-value comes to 0.0149. So that's step 3, and then step 4 is to make a decision and draw a conclusion. And so the decision rule is it's always the same. it's reject the null hypothesis in favor of the alternative if the p-value is less than the significance level of the test. Otherwise, fail to reject the null hypothesis. So the significance level of the test, as usual, it's going to be 0.05. So we look at this number, this p-value, 0.0149 is less than 0.05, so we reject the null hypothesis in favor of the alternative. And so our conclusion is, so we're rejecting the null hypothesis in favor of the alternative, and so this data is providing evidence that the births are not randomly distributed over the days of the week, that the variation that we're seeing, that we saw in the plot when we looked at the data, this variation, it's just too great to be explained by chance. Okay, there's something going on here, and so the next step here would be to say, try and come up with plausible explanations for why that might be the case. So I'll leave you to think about why do we have births being much higher on a Friday relative to the weekend where births are considerably lower. So that's one example of a chi-squared goodness of fit test for frequency data. I'm also going to quickly run through a second example because it's interesting that we can apply this test to the same situation that we had in the previous chapter when we just had two categories. So remember in the last video we looked at the binomial test. So that's one test that we can use when we've just got two categories. But we can also use this test that we've just talked about when we just have two categories. And so for that particular situation, there's two possible tests that we can do. The binomial test, which we covered in the last video, or this chi-square goodness of fit test that we used, that we just covered. So I'm going to run through this example quickly, just so you can get used to the steps in the test again. So for this example, we're looking at the gene content of the human X chromosome. So we've got some data here, and this is actually we're going to need to create our variable. So what we're going to do is we're going to use this variable here, CHR, and if the gene in question is on the X chromosome, then there's an X that goes here. If it's not on the X chromosome, then there's something other than X recorded. So for example, this gene is not on the X chromosome. This one too is not on the X chromosome, and so on. So we're going to create this new variable here that's going to just have two categories. So I'll just set it up and then we'll take a look at it. Okay, so what I've done is I've created a new variable, and it's going to be equal to X if that gene is on the X chromosome. So for example, the first two are on the X chromosome. The next four are not, and so we're recording not X for the next four. Okay, and then we can go through the whole rest of the data set and match things up like that. But what I'm going to do next is I'm just going to tabulate our results. So turns out that on the human, the gene content of the human X chromosome, there are 839 genes that are on the X chromosome and 18,789 genes that are not on the X chromosome. And so the test that we're going to do here is, because the X chromosome represents 5.2% of the DNA content of the entire human genome, that's going to tell us our null hypothesis here, because we're going to test whether the population proportion for on the X chromosome is 5.2%, and then the population proportion that's not on the X chromosome, the test value is going to be what would that be, 94.8%. Okay, so first step in the test, set up my null and my alternative. So my null is that the probability that a human gene appears on the X chromosome is 5.2%, and we're just saying it's either on the X chromosome or it's not, and so that implies that the probability that it's not on the X chromosome is 94.8%. And then the alternative hypothesis is that the probability that a human gene appears on the X chromosome is not 5.2%. So that's these numbers here. So 0.052 on the X chromosome and 1 minus 0.052 not on the X chromosome. Sorry, did I say that right? 0.052 on the X chromosome and 1 minus 0.052 not on the X chromosome. Okay, so we'll run the same code as we did before, just with our new data set and our null hypothesis values stated for the population proportions P. And again, we can look at the data. So this just reproduces the table we looked at earlier. What would we expect to see if the null hypothesis was true? So if we figure out 5.2% of the total number of genes that we've looked at, which is well, it's whatever the sum of these two numbers is. Uh, 19,628. So if we did 5.2%, 0.052 times 19,628, we would get, this is what we would expect to see if the null hypothesis was true, and this is what we would expect to see for the number of genes not on the X chromosome. Okay, and then to calculate the chi-squared test statistic, remember we're looking at the difference between observed and expected. Observed and expected. We square that difference, we divide it by expected, and then we do the same for the other category, observed minus expected, square that difference, divide by expected, and then we add those two numbers up, and that tells us our chi-squared test statistic. So let's take a look at it. So it comes to 31.105. So that's step 2, that's our test statistic. And then step 3 is to figure out the p-value. In this case, we've got two categories. So the degrees of freedom is 1 less than 2, which is just 1. And then the p-value is the upper tail area to the right of our test statistic. And it's a very small number. 5.2 times 10 to the minus 9, it's pretty much 0. So that brings us to, so that's the third step, and then the fourth step is make a decision. Is this p-value smaller than our significance level 0.05? Yes, it is. So we reject the null hypothesis in favor of the alternative and draw a conclusion. And we can say that it appears that the probability that a human gene appears on the X chromosome is not 5.2%. Okay, we got something, what did we get? We got a number that was considerably less than what we expected. Okay, so there's significantly fewer genes on the X chromosome in humans than would be expected if that null hypothesis was true. So there we go. So that's an illustration of how a chi-squared goodness of fit test works when we just have two categories. Okay, so in this video I've covered the chi-squared goodness of fit test for frequency data.